Alright, hello everyone. Since we didn't have the discussion last time, I decided to put together a video to give you some hints about the solution of the homework. So the first one, we want to use first Castigliano's theorem to find the rotation at B. And this is B, first of all. So regarding first Castigliano's theorem, all we need is energy as a function of degrees of freedom, right? By degrees of freedom, I mean the minimum number of displacement or rotation components that specify completely the deformed shape of the structure. Right, so the first step for the first Castigliano's theorem is always to label the degrees of freedom. Right, so in this beam I have these two fixed. So I start by looking at the nodes, right? Similar to the truss case, but in the frame and beam case, we can have rotation instead of just nodal displacement. So in a truss, the degrees of freedom would be the horizontal and the vertical displacement of the nodes. For a beam or a frame, so let's say if this is a beam, so for a beam or a frame, you just have you can have a delta and a rotation at the nodes. Alright, so let's look at this node here. So this node does not have any rotation and it doesn't move vertically because it's a fixed end, so delta is also 0. But this node, although it doesn't move vertically, which means delta is 0, but we do have a rotation, right? So you can notice that the direction of rotation is positive in the counterclockwise direction because your coordinate system is this, and this is the positive slope in this coordinate system. Again, this node is also fixed, and there is nothing to be considered here. So now, how do we write the energy of each of these two segments as a function of the nodal displacements that we have at each of their ends? So for the first Castigliano's theorem, we only need the energy for a segment. You can look up the derivation of this equation in the lecture notes. So this becomes 2 times EI over L, theta 1 squared plus theta 1 theta 2 plus theta 2 squared minus 6pi delta over L squared theta 1 theta 2 plus 6pi delta squared over L cubed. So you can look at this like a template energy equation. I say template because it's like for a general segment that has a rotation on the left, a rotation on the right, and a differential delta, which is like this. So if the left and the right side move by the same delta, there will be no distortion in the beam, right? So if this is the original segment and both ends move by delta, there is no distortion and there would be no energy stored. But if you have a differential delta, then there is definitely going to be energy stored in the structure. Alright, so let's see the situation for our beam. So if I put it right again, so we had two segments, one was L. Note that the EI for this is 2EI, the EI for this is EI, and the length of this segment is 2L. Alright, so I call this segment 1, I call this segment 2, and this was fixed. So for segment 1, I want to use this template here, right? So for segment 1, I see that based on the template, theta 1 is 0 because this is a fixed end, right? But theta 2 is actually the value of this state. So for segment 1, I get U equals to 2EI because this stiffness is this EI, 2EI over the length, note that is 2L. So for the length in the template, you have to actually substitute the value from your segment, which is 2L. So 2 times 2L. So sorry, becomes just 2L times. So theta 1 in the template is the rotation of the left of the segment, which is 0. So we have 0 plus 0 plus. Now theta 2 is just this theta here, so theta squared. Do we have differential delta for this? So you can see the right end does not move up or down because of this pinch support, and the left end, again, the left end doesn't move up or down, so you have delta 0 for segment 1. So you have minus 0, which I am substituting in this, and again substituting in this, you get again 0 plus 0. So that's the energy of segment 1 as a function of degrees of freedom. So what about segment 2? So for segment 2, I just have different EI and L. And now the left side has the rotation. So I get 2 times 2EI over the length is L over L. So I'm using the template, this template here. Times 0 plus, oh sorry, theta 1 is now theta squared plus 0 plus 0, right? Minus, again, if I look at the left and right side of the segment, so this is the left side, this is the right side, I don't have any differential delta, so the contribution of these deltas to energy are 0, right? So I have U1, I have to sum it with U2, and I get the total energy of the structure. That would be EI over L theta squared plus 4EI over L theta squared. So you see, now we have U as a function of theta. What we can do now is use first Castigliano's theorem. First Castigliano theorem, which says that if you compute the derivative with respect to the degree of freedom, this should be equal to the force or moment applied in the corresponding degree of freedom. Where did I get this negative? So if you look at the original problem, which is here, you can see that the external moment is applied in the clockwise direction, but the direction of our displacement, our rotation was positive in the counterclockwise direction. So you need the negative to account for this difference. So all you need to do now is compute the derivative of this with respect to theta and set it equal to m naught. You get theta, which I leave to you guys. Let's look at the second problem. So here you can see what we are looking for is the rotation at points D and E. Rotation at D, rotation at E. And again, similar to the logic that we had for the other one, you can see that none of these points have any degrees of freedom, right? Because they are fixed. So all the degrees of freedom that you have are theta E and theta E, theta at D. So you have 2 degrees of freedom, right? So your U should be a function of theta E and theta D, right? All right, so let's start. So again, we bring the template equation and put it in front of us, and we proceed segment by segment, writing the energy terms. So the left one I call segment 1, segment 2, segment 3, and segment 4. So for segment 1, this is fixed, but this end has theta E, right? Now, since the question is saying that we should neglect axial deformations, right? So the middle point, which is here, cannot have any delta in the horizontal direction or delta in the vertical direction. Because if it has any of these two deltas, then it would mean that one of the members is getting shorter and the other is getting stretched, and we cannot have that based on what the question is saying here. So we assume these two to be negligible, which is 0. So this point does not go up or down, so you don't have any differential delta again, so these two terms will be 0 in all cases. So you have 1 theta D and 1 theta E. All right, so if I want to write the energy for this one, so I can write U1 equal to, so in the template I have EI, which means the EI of the segment, so I should write 4 EI because this segment has EI of 4 EI over 2 times 2L. You see, length of the segment is this. Now theta 1 is the theta to the left, 0, so these two become 0 for this member. I only have theta 2, which is theta E. So theta E squared minus 0 plus 0, which is the contribution of these two, is 0 because delta is 0. Okay, so let's move to the next segment, 2. So 2 has a rotation theta D here, the length is 4L, 2EI is the stiffness, and you have theta E on the other end. So U of 2 is 2EI over 2 times 4L times, now you see you both have theta to the left and theta to the right, so you have theta D squared plus theta D theta E. I'm going off of the template equation, so theta E squared. Again, you don't have any deltas, so these are 0. 3, you have this little member only has theta E, so U3 is 2 times 2EI and L. 2EI over, oh, so there's no 2 in the template equation here, so please correct these 2's. So there's no 2 here, you just have L times theta E squared that's it. Now for the fourth one, again you just have 3L 6EI equals 2 times 6EI over 3L times theta E squared. So you can write total U as U1 plus U2 plus U3 plus U4. Now this will be a function of theta E and theta D, and you can get two equations by writing partial U partial theta D equals 0 because there is no moment here, and you can write theta or partial U partial theta E equals m naught positive because this m is in the same direction as theta. So you have two equations, two unknowns, you can easily solve it. Alright, now we'd like to move to second Castigliano's theorem. Well, as we saw, the first Castigliano's theorem, you write U as a function of displacements. Now, these displacements can be rotations as well. In this is the first. The second one, you write U as a function of external forces, which contains also concentrated moments, right? So Castigliano's theorem tells us that if you write partial U partial any of the pi, you get the displacement corresponding to that concentrated force. From conservation of energy methods, remember that we could easily write U as a function of forces like this. So 0 to, like let's say, over the length of a structure. I call this like len, which means the length of the structure n squared ds over 2EA plus over the length of the structure n squared ds over 2EI plus alpha s v squared over 2GA plus T squared over 2GJ. Alright, so again, mostly we will be dealing with axial forces and moments. So the first step again would be to compute the axial forces and the moments in all members of your structure. So let's see an example by looking at the homework problems. Okay, so here's an example. So we want to calculate the deflection at point B using Castigliano's second theorem. This is point B. So as you can see, we have no concentrated force applied at point B, right? Just for the solution of the problem, to be able to move forward with second Castigliano's theorem, we apply a force ourselves, call it P. At the end, we can set the value of P to 0. So P is kind of like a crutch for us to be able to solve the problem. All right, so we should start analyzing the problem for moments. We want to neglect shear, and for beams we never consider any axial forces, so we are just looking at the contribution of moment to energy. So we can write, so let's calculate the reactions first. So the resultant of this distributed load is W times L. So if you take the moment about the pin, just look at this right side, you have R, you have WL, so you take the moment about this point, WL times L over 2 equals R times L, so R is WL over 2. Now to calculate the moment for AB, I make a cut, so I have this P, right, and I have WL over 2 coming from the right side. So if I cut here at the place of the pin, you can imagine I'm cutting just a little bit to the right of the pin, right? So you have this P and you have WL over 2 coming from the right side, and I take my X from this point, right, and I make a cut somewhere here, right? If you cut here, moment pops out. Now if you take the moment about the cut, you get m of x equals negative px plus WL over 2 times x. Alright, now we can go ahead and write the energy for this segment of the beam. Well, what you might be asking, what about the segment BC? Now if you look at the energy term, you see that EI is in the denominator, and since EI for this member goes to infinity, it has no contribution to energy because this term becomes 0. This integral becomes 0 because EI is in the denominator, so you can forget about this member for this problem. Now a trick, not a trick, but something that simplifies the solution of such problems is that we know already what we want toward the end. We just want the derivative with respect to a force component, right? So we can, before substituting the moments, we can simplify the equation and directly write the integrals as, so I'm moving the derivative inside the integral, so this becomes n partial pi ds over ea. So you see, if you calculate the derivative of n squared, it becomes 2n partial pi, right? Similarly, for m, it becomes m partial pi over ei plus, well, you can get the ones for shear and torsion similarly. Alright, so if you plug in our moments in this and we neglect the axial forces, so we get partial u partial p is equal to the integral from 0 to L moment, which is WL over 2x minus px times the partial derivative of the same thing, which which is partial m partial p, which is negative x dx. Where now if I evaluate this, this becomes, well, at this point I can actually go ahead, because p has played its role, we are done with it. We can right here put its value equal to 0. So this becomes integral 0 to L WL over 2x negative x over E, which is equal to WL over 2EI x squared root negative WL to the 4th power over 6L. Now, does it make sense that it's negative? You see that the distributed load was applied in the upward direction, so we expect this point to go up, which is in the opposite direction of P, so the negative makes sense. Alright, now let's look at a case that has one of these springs in it. So we want to use the second Castigliano's theorem, right? The procedure is very similar. So here we only have bending. So again, we directly use the formula that already has the differentiations inside the integrals. So what are we looking for here? Deflection at point B. So fortunately, there's already a force applied at B in the direction that we want the deflection. So partial U, partial P should be equal to the corresponding delta that you are looking for. But we know that this is equal to the integral from 0 to L m partial m over partial P over EI dx plus the contribution of this spring. Remember that this is not directly the energy, right? So for a spring, here is a side note, for a spring, the energy of a spring is half of F squared over K, which is the stiffness of the spring, right? What we want is partial U, partial P, right? So I have to actually calculate the derivative of the energy of a spring with respect to P, which becomes F partial F. So F is the force in the spring. Force in the spring. Something we calculate as a function of P. So we'll see how we calculate that soon. Partial P over K. And that's it. So using this side note here, you can write F partial P over K, right? Okay, now let's go about actually solving our problem. So if you look at the beam, so you have a P here. If you write sigma F in the y direction equals 0, what you get is that the single force P should be here. So this would mean that there's a compression on the spring, right? Spring with Ks. Also, there's a moment here which is equal to PL. So if I take my x from here, m of x is going to be equal to negative px, right? We can make the cut here. There will be a moment. It's better if I don't show it like this. So if you make a cut, P, m becomes negative px. If you take the moment about this point, right? So now we can easily use the formula partial U, partial P equals the integral from 0 to L m times the derivative of m with respect to p, which is negative x, over EI, plus, now we found that the force in the spring is actually P, so we write P partial F partial P, which is 1, over K, right? So if you carry out the integration, you get delta at B is equal to P over PL cubed over 3EI plus P over K. Now we can do a little bit of sanity check here. So you see the effect of a spring is in this part, the effect of the beam itself is in this part. So what does this mean? So we know that the force displacement relationship for a spring looks like this, right? And we saw that all the force P has actually gone into the spring. So we expect that we have P equals K times the displacement at the place of the spring. So this would mean that delta spring actually brings the whole beam down, right? So this is part of delta B. So, right? So in a rigid fashion, you can imagine that because of the flexibility of the spring, the whole beam comes down. But you also have contribution due to bending, which is the curved shape of the beam. So this is the spring part, equals P over K. This is PL cubed over 3, contribution of the bending of the beam. And the sum of these two gives you delta B.